Okay, so that is how you process a given Turing machine and a given input string. But how do we design Turing machines in the first place? Let's see a few examples. And we are going to see examples to recognize languages, one example to, I think, a few examples to do that. And we will see one example to actually compute an operation. And we will see how Turing machines are also capable of making computations. So here's an example again taken from the textbook uh, by Rosen. Find a Turing machine that recognizes the set of bit strings that have a 1 as their second bit. Essentially, this is the regular set 0 plus 1, 1, 0 plus 1 star. So the first bit is here. It could be either a 0 or a 1. The second bit, I want it to be 1. And the rest, I don't care. It could be done at that point, and it could be zeros or ones, whatever comes after the second bit, I don't really care. So my alphabet consists of zeros and ones, and we will see that 4 states suffice to design this Turing machine, and we will have one accepting state depending on my second bit here. Now let's see. I'm going to have an initial state S0, and S0 is going to, in state S0, I'm going to look at the first bit or the first symbol on my tape, which has a candidate string to be recognized or not. And I do not really care about the value of the first bit. So using S0, using either input 0 or 1, I'm just going to switch to another state that will indicate, okay, I have processed the first bit, now comes the second bit. So S0 with 0 goes to S1, S0 with 1 also goes to S1. I do not modify the content of the tape, and I move one position towards right. Now, I am in state S1, and this is the significant one because if I see a 1 here, I'm going to accept the string. If I see a 0, I'm not going to. So with a 0 input, I'm going to move to S2, which is a non-accepting state. And with an input of 1, I move to S3, which is the accepting state here, as described here. And again, I do not modify the tape content, and I move towards right. And afterwards, you are in either S2 or S3. If there are more symbols, you are in either S2 or S3. With S3, I do not really need to define any more quintuples because, well, the machine will simply halt in this case. And since S3 is accepting, the string will be accepted. And this one is given by Rosen in his solution. But again, similar to S3, this is not really a necessary quintuple here. You can simply not define any action when you are in state S2 because it's going to be a non-accepting state, and no other symbol coming after the second is going to change that. So this is really not really necessary, not necessary. You can have this rule, but you can also not have it. What about these last two? These are to avoid recognizing strings of length 0 and length 1 because I need the second bit to be a 1. So I'm not going to recognize the first bit or the string with length 0 or a length 1. So length 0 indicates I'm in state 0 because that's the initial state, and I immediately encounter a blank position, a blank symbol. So this means my string is empty. In this case, I need to go to S2, which is a non-accepting state, and I will stay there. And similarly, if I'm in state S1, indicating that I have seen the first symbol, now I'm looking for the second one, but I encounter a blank symbol, meaning that my string is of length 1 only, so I cannot accept this. Therefore, I need to go to the non-accepting state of S2. So this is how you design a Turing machine. And this should give you an idea about how to actually implement any finite automaton by a Turing machine. It simply suffices to actually scan the input string from left to right, one by one, and defining as many states as necessary without ever changing the contents of the tape, because a finite automaton is essentially a Turing machine without the tape. Well, since you do not remember the contents, essentially, so you can always design a Turing machine to actually implement a finite state automaton. Here's another example. This time you see we have a context-free language, 0 to n, 1 to n for n greater than or equal to 1. And this is not a regular language, but we will see how this can be recognized using a Turing machine. And these are going to be the strings of form 01 or 0011, 000111, 00001111, and so forth. Essentially, what you want to do is you mark the leftmost 0 and the rightmost 0 one by one, and you would like the markers to meet at the middle. If that is the case, you will accept the string. If that is not the case, you will not accept. So mark the leftmost position and rightmost positions using a symbol called M. So my symbols are going to be 0, 1, and M. Well, my inputs are not going to be not going to involve M initially, but I can use the symbol M to modify them and work your way towards the center of the string. Because I can move left and right, I can go to the end of the string and come back. For instance, the string 000111 would successively become, first you mark the first 0, and then you go to the end of the string and mark this one to become M, and then you come back to the first 0 and mark it, and go to the last one before your mark. So when you encounter this, you come one cell back and modify this one. And when you do that, you come back to this 0. Okay, so this is the one marked as M. You come back for this 0, mark it as M, and then you go for the final one, which is this one. When you have these markers meeting, then you know that this satisfies the required structure. So it will be accepted. Okay, if an unexpected symbol is encountered, for instance, when looking for the final one, you encounter a 0, or vice versa, and then you just move to a state that is not accepting and stay there, which means you will halt. The list of quintuples needed for this behavior is long. So the behavior is not that complicated. It's simple enough to understand. And you can even by yourself actually come up with the list of quintuples. But it's a long list because you need to consider a lot of situations. Even for such a simple operation, designing a Turing machine might be complicated.